Hey guys, Alexander here, and in this video I will be covering the exponential distribution, its characteristics, how to derive its expected value, the variance, as well as the moment generating function, and its memorylessness property. I will also show you what that means and how you prove it. So let's begin. If a random variable x follows the exponential distribution, then we say that x is distributed exponentially with the rate parameter lambda. This lambda is the same rate parameter as what we saw in a Poisson distributed random variable. And what an exponential distribution really measures, it measures the inter-arrival time for events that arrive in a stochastic process that follows a Poisson process or a Poisson distribution. So if I say that people arrive as a shop at a rate of lambda, which let's say people arrive at a rate with lambda equals to 3 people per minute arrive at the shop, then we'll say that, well, the number of arrivals is distributed as a Poisson random variable with lambda equal to 3 per minute. But the amount of time in between arrivals of individual people, that is going to be distributed as an exponential random variable with a rate parameter of lambda equals 3. So the amount of time between arrivals, or the inter-arrival time, will follow an exponential distribution with the same rate parameter. So this is to give you an idea of how we use the exponential distribution. We use it to model the time between arrivals. So let's start off with its probability density function, the PDF. This is equal to f of x, and we say it is lambda e to the negative lambda x, and x has to be greater than or equal to 0. The cumulative distribution function, the CDF, which is equal to capital F of x, which is equal to the probability that capital X is going to be less than or equal to little x, is equal to the integral from 0 to x of lambda e to the negative lambda I di. And we know that this answer is going to be 1 minus e to the negative lambda x. And this is the basics that you need to know. You need to be able to memorize the CDF so that you can quickly use it if you encounter this question in a test. So let's get to deriving the expected value. The expected value of x is going to be, for a continuous distribution, it is the integral over the entire support, all the values that this random variable can take. So in this case, it's going to be from 0 to infinity of x times lambda e to the negative lambda x dx. Don't forget your dx. And to do this, again, you're going to be asked to have to use integration by parts. So let's set u to be equal to lambda x. That means that du is going to be lambda, du by dx, of course. dv is equal to e to the negative lambda x. That means that v is going to be e to the negative lambda x over negative lambda. Now, we plug it into the formula that the expected value of x going to be equal to uv evaluated at the limits of 0 and infinity minus the integral of v du from 0 to infinity. And this we see happens to be u times v is negative x e to the negative lambda x minus the integral from 0 to infinity of v du, which is negative e to the negative lambda x. And now we need to evaluate these limits and carry out this integration on the right side. So the first thing that we can do, we see here's a negative sign, here's a negative sign. Let's make it a positive and let's evaluate this integral. So it becomes positive e to the negative lambda x divided by the derivative of this exponent, which is going to be negative lambda, and we need to evaluate it from 0 to infinity. And over on this side, we end up with a limit as x goes to infinity of negative x over e to the lambda x minus 0, because we can see at the limit of 0, x is 0. That means that this product is going to be 0. So for this limit, you see that both are going to converge to infinity as x goes to infinity. So we're going to have to use L'Hopital's rule. And so that means we're going to take the first derivative of both of these. So we end up with negative 1 over lambda e to the lambda x. And the limit of that as x goes to infinity, we can see this bottom, the denominator is going to converge to infinity. So that means that this whole fraction is going to go to 0. So it's equal to, the expected value of x is thus going to be equal to e to the negative lambda x over negative lambda evaluated at these limits. So what we can see is that this exponent should be brought to the bottom. So the first one is going to be the limit as x goes to infinity of 1 over negative lambda e to the lambda x. And we know that this is equal to 0. And we have to subtract 1 over negative lambda e to the lambda x evaluated at x equals 0. And we know that this is simply going to leave us with the expected value of x. Negative and a negative becomes a positive. Plug 0 in here, that becomes e to the lambda times 0, which is 1. So we're left with 1 over lambda. So there we have derived the expected value of x if x is distributed as an exponential random variable. Now it remains to derive the variance. And we're going to again make use of the fact that the variance of x is equal to the expected value of x squared minus the square of the expected value of x. Now we have derived the expected value of x. Let's get the expected value of x squared. And this is simply going to be the integral from 0 to infinity of x squared lambda e to the negative lambda x dx. So let's write this down. We let u be equal to x squared lambda. That implies that du is going to be 2x lambda. We let dv be equal to e to the negative lambda x. That means v is going to be e to the negative lambda x divided by negative lambda. And again, when we apply this formula for the integration by parts, we get the expected value of x squared is uv evaluated at its limits. So it's u times v, which leaves us with negative x squared e to the negative lambda x evaluated from 0 to infinity. And we're going to be subtracting from it the integral of v du, which is going to be equal to negative 2 x lambda e to the negative lambda x divided by lambda. So we see that these lambdas cancel. This negative and this negative multiply out to make a positive. We can bring this 2 out, and then we're left with xe to the negative lambda x and this expression on the left hand side. Now there's something very important that I want to bring to your attention here. A student that is good at calculus will go and evaluate this. A student that has common sense will say, well, this looks oddly familiar. Didn't I see something like this before? And you did. It was the expected value of x is this same thing, except there's a lambda in it. Here we just don't have the lambda. So how can we do that? How can we solve that? Well, and don't forget your dx, of course. Let's multiply in by lambda, and then we divide over here with lambda. And we know that this is simply then going to be the expected value of x, which we have derived, and we know the value is simply 1 over lambda. So there's no need to go do more integration by parts. You just use something you have derived already. And this will help you to save time. And it is a common technique, a very common technique that you can apply for continuous distributions when you're deriving their moment generating function, when you're deriving the expected value or the variances. Use this technique by trying to see if you can make this integral into the form of something you know already, into the form of the expected value or the form of a probability, the cumulative distribution function over all of the range. And I'll show that to you in the moment generating function part. But always try to get it into a form that you have seen before to simplify the amount of work you've done. Well, we know that this is integral. We'll then evaluate the expected value of x, which is 1 over lambda. So we know that the right-hand side over here is simply going to be 2 over lambda squared. For this expression, we need to evaluate its limits. We know already that at 0, this is simply going to be 0. So we already know it's going to be plus 0 for the second part. But the left-hand side, we need to find the limit as x goes to infinity of negative x squared over e to the negative lambda x. And we're going to have to apply L'Hopital's rule twice here because we have an exponent of the second order here and we have an exponential at the bottom. But eventually we'll get the answer that this limit is 0. So we're left with the expected value of x squared is going to be equal to 2 over lambda squared. You can go evaluate this for yourself by taking the derivative twice of the numerator and the denominator as well. And then plugging in the limits as x goes to infinity, you'll find the answer converges to 0. So this is the answer for the expected value of x squared. But we're trying to find the variance of x. So the variance of x is equal to the expected value of x squared minus the square of the expected value of x. So it's equal to 2 over lambda squared minus 1 over lambda squared, which leaves you with 1 over lambda squared. So we have the expected value, we have the variance of x. Congratulations. And you learned a new technique, or not a new technique, this is common sense once you've seen it. But common sense is not all that common, and by practicing you can make your life easier. And this is a trick that you can use typically in a lot of the continuous distributions, is to try to identify things that you have seen already in this integral that will allow you to easily derive results. Now, I told you I would also show you the moment generating function, so let's do that as well. So phi x at t is equal to the expected value of e to the tx, which is going to be equal to the integral from 0 to infinity of e to the tx of lambda e to the negative lambda x dx. And we can group this and see that it's going to be, put the lambda outside and keep these guys on the inside. It's going to be e to the negative lambda minus tx dx. Notice that you see that here something looks awfully familiar, doesn't it? You have a lambda in this exponent part here, because you have lambda minus t, but let's call this lambda nu. Let lambda nu equal to lambda minus t. Well, we know that the integral from 0 to infinity of lambda e to the negative lambda x dx is equal to 1. We have this part, but we need the lambda. So we're going to have to multiply by a lambda nu and divide by a lambda nu. So I'll show you what that means. So we're going to have lambda over lambda nu times the integral from 0 to infinity of lambda nu e to the negative lambda nu x dx. And we know that this is simply the integration over all the possible values that the probability density function of an exponentially distributed random variable can take. And we know that this is simply going to be 1. So that means that phi x of t, which is equal to the moment generating function, is simply lambda over lambda minus t, and this is for t has to be less than lambda for this to work. So there, you've derived your moment generating function in 3 lines essentially, and you didn't have to do any integration at all. So this is the trick that you have to look for when you're doing deriving moment generating functions, deriving variances for continuous distributions. Always try to look at the integral, try to associate it with a form that you know. In this case, we had the e to the tx times e to the negative lambda x, which we know is simply going to be e to the x times t minus lambda, but we know that the form of an exponential distribution's probability density function is lambda e to the negative lambda x. So multiply with a minus at front and switch the order of these two. So it becomes lambda e to the negative lambda minus tx. And then you see that we need a lambda minus t in the exponent part to have it look like lambda e to the negative lambda x. So we transform this. We have transformed this equation into lambda over lambda minus t over the integral from 0 to infinity of the PDF of an exponential distributed random variable with lambda minus t as its rate parameter. So we changed the rate parameter and we divided by a constant here so that we could avoid having to do integration. So make life easier for yourself. Try to see if you can find results that help you have to avoid integration, because we make mistakes when we do integration. We make mistakes when we do more work. So to lower your chance of the frequency of things going wrong, do less things. Make sure you do less work. And by doing so, by working smarter, you can derive the results. You can derive the moment generating function. So that's how we get the moment generating function, the variance, and the expected value of a Poisson of an exponentially distributed random variable. The last thing that remains is a comment about the memorylessness. Now, the comment that I would like to deliver about the memorylessness is that the probability that x is going to be larger than s plus t, conditional on us having already waited for more than s seconds. This is simply equal to the probability that x is larger than t. And I'll first show you how we derive this, and then I'll show you the intuitive way to think about it. So this can be written as the probability that x is greater than s plus t, intersection with x being greater than s, conditional on the probability that x is larger than s. And we can do this by Bayes rule, because we have A given B, so it's A intersect B over the probability of B. And this intersection is, if you've already been waiting for longer than S plus T, you've already been waiting longer than S. So this simplifies to the probability that X is greater than S plus T, conditional on the probability that X is greater than S. And this is equal to, we already derived the cumulative distribution function over here, 1 minus e to the negative lambda x. But we have to, this is for the probability that x is less than or equal to x, so we'll have to take 1 and subtract this result from it. So it is equal to 1 minus e to the negative and lambda s plus t divided by 1 minus e to the negative lambda s. And you see that this resolves, if you solve this, the answer that you get is e to the negative lambda t. And this is equal to the probability that x is greater than t. So what the memorylessness means is that given that I have waited already for a time longer than s, the probability that I'm going to wait an additional t seconds, given I've waited for more than s, is going to be the same as just starting from the beginning and saying, what's the probability that I'm going to wait an additional t seconds? So the easiest way to think about this is if you go shopping with your mother. If you go shopping with her, the probability that you're going to be waiting for, let's say we've waited already for half an hour, 30 minutes. What's the probability that our waiting time is going to be greater than 30 plus 10 minutes, given we have waited already for 30 minutes? This is simply going to be equal to the probability that we are going to have to wait for her for more than 10 minutes. This is what it essentially boils down to. The memorylessness means that the distribution, the conditional distribution over any interval of time, the probability that you have to wait a certain amount of time over any particular interval is the same. That conditional distribution is the same. So this is probability that x is greater than 10. This is going to be the same as asking what's the probability that x will be greater than 40 minutes plus 10, given that x is already been greater than 40. This is still going to just result in the probability that x is greater than 10. The distribution doesn't care how long we have waited already. Your mother doesn't care how long you've waited already. If the probability that she's going to wait for more than 50 minutes, given you've waited already for 40 minutes, is going to simply be the probability that your waiting time is greater than 10. So that's the memorylessness. So that wraps it up for the exponential distribution. The key takeaways that I'd like to ensure you know is, I'd like you to remember these tricks. The tricks for avoiding to do more integration than you need to do for the expected, for the variance, for the expected value of the x squared, by simply arranging this into a form that you've seen already. And the same story over here for deriving the moment generating function. This approach is going to be seen all over the continuous distributions. Use the fact that this is just another, can be seen as just another random variables probability distribution function. Transform it in a form where it can be lambda minus t times e to the negative lambda minus tx, which is just the integration over the probability mass function of an exponentially distributed random variable with a rate parameter of lambda minus t. And we know if we integrate over the entire support, then this integral is just going to be 1. And then we're going to be left on the left-hand side with lambda over lambda minus t. And you'll be able to use this in the gamma distribution as well, and the normal distribution, and I will show you those in later videos. Thank you for paying attention throughout this video. Good luck with your studies in statistics. Alexander, out.